This assessment asks us to predict the product of the reaction of the same alkene with HBr and HCl. As always, when we're predicting a product, we want to do this by drawing a mechanism of the reaction. What we recognize is that the alkene is nucleophilic and HBr is a good electrophile. And so we can show an acid-base reaction where the pi electrons grab the proton, kicking out Br-. This is going to result in the formation of a tertiary carbocation. Why? Because the tertiary carbocation is more stable. We could have also used our bouncing arrow to show formation of that tertiary carbocation more clearly. By starting in the same spot, we can have the electrons bounce through the secondary carbocation and attack the proton there. This makes it clearer that we're forming the new CH bond at the secondary carbon, and the tertiary carbon is becoming the carbocation. The other product of this reaction is Br-, and now we have the standard negatives attack positive situation where the lone pair is donated to the tertiary carbocation to give us the following product. How does this reaction change when we use HCl? The answer is hardly at all. We can show the deprotonation step, pi bond grabbing the proton, kicking out Cl-. Once again, we'll make the tertiary carbocation because it's more stable than the secondary carbocation. Cl- is our other product here. And so now Cl- will donate its pair of electrons to the empty p orbital represented by the carbocation to give us, in this case, a tertiary chloride. Identical reaction mechanisms regardless of which reagent we use. To complete this, let's go ahead and show the bouncing arrow that we might have used down here in the HCl reaction. So once again, we can have those pi electrons bounce off that secondary carbon and attack that proton to make it more clear that we're forming the new CH bond at the secondary carbon, and that the tertiary carbon is losing the electrons and is therefore positively charged.